Hey guys, so this is just going to be an explanation of Le Chatelier's principle, which is a very important part of chemical equilibrium. Yay, let's begin. So concentration. If you increase the reactants, then the reaction will shift to the right. If you decrease the reactants, then the reaction will shift to the left. If you increase the products, the reaction will also shift to the left. And if you decrease the products, the reaction will shift to the right. And the equilibrium constant K doesn't change because it's constant. And here we're just simply changing the concentration of products or reactants on one side of the equation. So there's no outside factors that are making the reaction proceed in one way or the other. So in this example, we have 2 moles of SO2 and 1 mole of oxygen yields 2 moles of SO3. And if you were to increase the SO2 on the reactant side, then there will be more SO3 formed. And if you were to decrease the product, SO3, then the reaction will shift to the right because there's less products, so there has to be more products produced to make it reach equilibrium again. So pressure and volume. It's important to remember that these two are inversely related. So if there's an increase in pressure, then there would be a decrease in volume. And if there's an increase in volume, there means there's a decrease in pressure. So if there's an increase in pressure or decrease in volume, and more moles of gas are on the left, then equilibrium shifts to the right. If there is an increase in pressure or decrease in volume, and more moles of gas on the right, then equilibrium is shifted to the left. If there is a decrease in pressure or increase in volume, and more moles of gas on the left, then equilibrium shifts to the left. Lastly, if there is a decrease in pressure or increase in volume, and more moles of gas on the right, then equilibrium shifts to the right. And the equilibrium constant K doesn't change. In this example, there is 1 mole of nitrogen gas plus 3 moles of hydrogen gas yields 2 moles of ammonia. So it's important to note that there are 4 moles of gas on the reactant side, 1 mole of nitrogen gas plus 3 moles of hydrogen gas, and there's 2 moles of gas on the product side. So in this problem, if you were to decrease the volume, then the equilibrium would shift to the right because just think of it as if there's 4 moles and they're in a small space, they would probably want to change into a state that takes up less space to compensate for the smaller volume that they're in. So in this case, they would probably want to convert into more products since there's only 2 moles of that compared to the 4 moles of the reactants. So if there was an increase in volume, then the molecules would want to change into a state that takes up more space to compensate for all this room they have. So the equilibrium would shift to the left or to the reactants because there's 4 moles on that side, so that would kind of balance it out so that there's more room, so now they can produce more reactants so that they can reach the equilibrium. So temperature, the equilibrium constant does change, and this is because temperature is one of those outside factors that really strongly influences the direction that a reaction goes in. I made this chart to kind of simplify the relationship between the change in heat and temperature and the resulting shift and increase or decrease of K. For the first one, if a reaction requires heat, which means it's endothermic, while forming product, then increasing the temperature will favor products and equilibrium will shift to the right, and K will increase as a result. And this is because if the temperature increases and the reaction's endothermic, that means that it's the heat will help the reaction go forward and make products because the reaction requires heat to make products, so it'll shift to producing products, of course, and this results in an increase in K because there's a higher concentration of products. And K is the concentration of products over reactants. So bigger, bigger product concentration would increase K. Now, if a reaction gives off heat or is exothermic while forming product, then increasing the temperature will favor reactants and equilibrium will be shifted to the left and K will decrease. So an interesting way of thinking of this is if the reaction itself is exothermic, so to go from reactants to products, it's exothermic. Then to go from products to reactants is the opposite, or endothermic. And so that means the reason why if you increase the temperature, it'll shift to the left or to the reactants is because it's endothermic from products to reactants. So the increase in temperature will be breaking apart the products into more reactants, which results in that shift to the left. And that, of course, increases the concentration of reactants and results in a decrease in K. If a reaction requires heat or endothermic while forming products, then decreasing the temperature will favor products and equilibrium will shift to the left and K will decrease. So just like in the other point, if it's endothermic going from reactants to products this time, then going from products to reactants, that means it's exothermic. So a decrease in temperature will favor products to reactants. So there will be a shift to the reactants because decrease in temperature kind of matches with exothermic, which is products to reactants. And this results in a decrease in K because of the higher concentration of reactants. So lastly, if the reaction gives off heat or is exothermic while forming product, then decreasing the temperature will favor reactants and equilibrium will shift to the right and K will increase. So in this case, the reaction from reactants to products is exothermic, and if you decrease the temperature, that favors products because it fits the exothermic. So there's going to be a shift to the right or to the products, and higher concentration in products means an increase in K. Also, on a side note, I put positive and negative signs to correspond to certain words to kind of make it easier to remember visually. So the positives are associated with forward or increasing or adding, and negative signs are associated with subtracting or going backwards or decreasing. So endothermic is positive because you're adding heat, and increasing is obviously positive because you're increasing, and to the right is kind of like going forward to products. It's kind of reactants to products kind of seems positive, and conversely for decreasing, exothermic giving off heat, so you're subtracting, and going to the left is like going backwards, and decreasing is going down. So if we continue to look at it mathematically, you see endothermic positive times increase positive equals to the right positive and increase is positive. And exothermic negative times increase positive equals to the left negative or decreases negative. And then for the last one, exothermic negative times decrease negative is like saying equaling a positive to the right and positive increase. Just a neat way to remember it visually. So in the first example, you know it's endothermic if they give you a delta H, which is positive. Doesn't matter what the number is as long as you know that it's positive kilojoules or joules. So if you were to increase the temperature of this reaction, then the reaction would shift to the right and form more products because increasing heat is needed to break apart the reactants into products, which is the definition of an endothermic reaction. So this second example is a little different because I saw it in the book and it didn't give you a delta H. However, you can assume it's endothermic because it gives you a chlorine molecule breaking into chlorine atoms on the product side. So for it to be able to break into those chlorine atoms, it requires heat, which means it must be endothermic. So this last example is an example of an exothermic reaction because it's given that the delta H is negative, which means that heat is being lost. And so if you were to decrease the temperature, then that would result in a shift to the right or more products being formed. So thanks for watching, guys. I hope I wasn't too confusing. Sorry about my stuttering. Um, Good luck on your finals.